Good morning. This research work deals with the exergy analysis of the alluvial gold mining process. Mining sector has definitely helped to develop the economy and infrastructure of many commodity exporting countries. Nevertheless, when those activities are not carried out in a sustainable way, it may endanger the conservation of the delicate ecosystem in which their extractive activities are undertaken. Currently, accelerated mineral extraction and utilization rates seem to rely on the misconception of limitless resource availability. Oftentimes, mass-based or monetary indicators are used to measure and explain the commercial and environmental impacts of extractive activities, but they cannot evidence the increasing energy consumption required due to depletion of the natural resources. Thus, in this work, a second law-based analysis at both the plant-wide and component level is proposed for the alluvial gold mining process. This study aims to shed light on the sub-processes responsible for the main energy degradation, quantified by the exergy destruction rate and other three exergy indicators, as it will be explained later. As the concentration of gold ore tends to zero, the energy consumption in its beneficiation may reportedly increase in up to 3 orders of magnitude. Thus, as concentrated deposits are depleted, ore production becomes unaffordable in the limit scenario of ore grades declining to crustal concentrations. When different sources of energy are consumed to produce a substance, in this case gold, it will be more rational if the second law analysis is used, as it can assign different degrees of quality to all the different energy inputs, regardless of its nature, namely fuel, heat, electricity, or non-fuel substances. The alluvial gold mining process starts with the removal of the topsoil, a layer of at least 20 meters depth, before the clay containing gold can be extracted and processed by using gravity extraction methods. These methods capitalize on the difference of density between gold and sediments, employing spoon dredgers and other devices to obtain a sort of slurry that is then sent to the metallurgical extraction process. Therein, both physical and chemical separation processes are carried out in order to obtain a high purity gold product and a ferrous material byproduct as a result of the gold extraction and cleansing processes. Some of those byproducts are not profitable and must be treated in a set of wastewater treatment plants and stored in large tailing ponds while awaiting for final waste disposition. On the other hand, the gold-rich stream needs to be melted and molded before it can be commercialized. Due to the presence of very different nature of separated components, such as mineral, soil, wastewater, in different amounts and compositions, using only one indicator for calculating the exergy performance would not be reliable. In fact, some indicators may not apply due to the absence of gold in some waste streams. In this slide, the useful exergy efficiency, the separation exergy efficiency, and the extraction exergy intensity indicators are defined. The first one aims to determine the gross ratio between the useful outputs and the overall process inputs, whereas the second one attempts to quantify the gain on chemical exergy due to the separation process. The last one aims to compare the exergy only of the gold produced with that exergy of the inputs to the process. This slide shows the Grassmann diagram representing the exergy flows in the alluvial gold mining process, including the energy inputs, the gold-rich streams, the inerts or gold lean flows, and the exergy destruction in each production step. The overall useful exergy efficiency, as well as the separation exergy efficiency and the extraction exergy intensity of the overall processes, are also reported. As it can be seen, the extraction exergy intensity indicator remains lower than 1% throughout the separation process, showing a rather intensive and inefficient production process. Some processes, such as the trommel, physical separation, and drying systems, are more efficient than the chemical separation and wastewater treatment counterparts. Accordingly, utilization of more environmentally friendly treatment processes and electrification of the primary movers of those installations may help increasing the overall efficiency of the process, but only a very marginal increase in performance could be expected, as the mineral resources depletion renders the gold extraction process an unprofitable or at least an environmentally unfriendly application. We would like to acknowledge our funding institutions, the National University of Colombia, and the last author would like to thank the Colombian Administrative Department of Science, Technology, and Innovation. Thanks for your attention.